Hello everyone. Who's with me? Cool. Um, yeah, this is just a funny image to start things with. So hello DeConf, and today we are here to talk about the day we reverse engineer a Game Boy Advance game. I'm Matheus, as Y the Combinator, and here's Macabeus. And the first thing everyone asks is, what the hell? What do you guys mean by doing this? And let's do this raise your hands thing, and just for me to know, who here knows this thing on the left side? Yeah, just like I thought. No one. But I bet that most of you know this game console on the other side, which is Game Boy Advance. And everything started when we were playing this. This is the emulator, but we were playing this game, Klonoa, in the Game Boy Advance emulator. And this was Macabeus and me. And this was us playing Klonoa. And we got bored. And yeah, this is us bored. Because basically, Macabeus wanted to play more levels, and I didn't like the levels at all, so I wanted to play different levels. And then we decided, okay, let's do some mad science things. And because actually working on personal projects is just a very nice way to learn stuff that you normally don't learn on your daily basis. For example, I'm a front-ender and he's a full-stack developer. We don't usually play with reverse engineering, for example. So, yeah, and this is Klonoa. For those who don't know Klonoa, this is what the game looks like. There's no sound because it's just very, very annoying, the music playing in the background. But it's a tile-based puzzle game, and many people actually love to play it. And it's got just 3 levels, and we thought, okay, why don't we create more? And this is how CloGBA.js was born. And CloGBA.js is a web application which allows you to write more in the detail levels that you have on Klonoa, and it's open source on GitHub. This is the link, and it's basically a React application with some parts in JavaScript and some parts in C code. But how everything began? So reverse engineering, I think, is such an abstract thing. There's no certain path for you to follow, and you don't basically know, okay, I'm going first doing this, and then this, and then this. So we decided to just stretch a simple bridge, because in reverse engineering, modifying something that already exists is way simpler than deleting or creating something from scratch. So we decided, okay, let's stretch a bridge that we have in a level. And we use mostly 2 tools. The first one is NoCacheDBA. And NoCacheDBA, it's got very useful tools for doing dynamic analysis, which is basically analyzing the code as you run the software, in this case, as you play the game. And the other one is IDA, and IDA basically fits some things that NoCacheDBA lacks for doing static analysis. So, for example, it allows you to have a graph visualization of your assembly code, and even simple stuff like commenting the lines of code you can also do with IDA, so it was quite helpful too. And these are the 2, one each side. And here we are using virtualization on the Mac because you just have them for Windows. And let's start to stretch the bridge. And this is the panel that we have on NoCacheDBA. And here we are in the first level of the game. And the bridge that we want to stretch is here. I'm going to highlight it. And this is the tile ID for the bridge. As you know, on a tile-based game, each tile has a very specific unique ID. So this is the tile ID for this part of the bridge, and there's also the ID for the other part of the bridge. And here we can see the memory address where this tile is located, which in this case is 0600F1AG. But the funny thing is that this is not surprising, and this is not surprising. Here's the manual that we have online for explaining everything under the hood, the Game Boy Advance architecture. And reading the memory, we found that in the memory we have many regions that each region has a very specific function, and that address we found is in a region called VRAM, which stands for video RAM, And the purpose of this region is to store sprites in the backgrounds. So as I told you, it's not surprised that we found our bridge there. And if we go to the memory address, we see that each part of the bridge is over there. And so now we can grow it bigger. And if we run this, we see that it was bigger, but there's something puzzling. Once we went to the next frame, the new part just disappeared. So this was one of our first "what the hell is happening here" moments. And to understand why this is happening, there's a very important concept behind it, which is called the DMA, and I guess Macabeus can tell us a little more about that.
Yes, Matthias, these behaviors make sense. And in order to understand why it makes sense, you need to understand an important concept about Gameboy Advance, the DMA. Moving Klonoa to another place of the level, we can see that the entire time map changes on video run. So we can note that it will only store what the player has to see from somewhere else that has the entire tile map. But where is the entire tile map in order storage in order to send the information to video run for each frame? There is a book that explains many details about the internals of GBA, and in the tiles map chapter, it contains an important concept: direct memory access, DMA. Well, this is a feature of computer systems that allows certain hardware to access main system memory, regardless of the CPU. Using other words, it provides a way to copy and paste faster. It makes sense because the video run is too small to store the entire tile map. Then it's necessary to store the entire tile map on another region and send a part of it to video run. And Nocache has a feature that allows to track the DMA communication. One frame on the game, we can see that it made 4 copies. And on the results, this is the closest to the base of the bridge. And this is the address of the video run data source. So GBA replaces the video run with the another data started from this batch, which is located in a region called flash WRAM. That is a large one. So instead of change the batch as the video run, we need to change the bridge batch as the flash WRAM. Okay, let's go to address. And our bridge starts here. Nice, we found it. So let's switch it. Since DMA we send the tile map data from to video run on each frame, it's working now, right? Let's see it. What? We can see the tiles. They are on the screen, but you can't stand on them. It's crazy. Why you can't to stay on these new tiles? Doing a very simple test, walk to another part of the level, you can see that all extra tiles disappear when out of the play visual range. So there is another memory region that really stores the entire tile map and is the data source of the flash WRAM. But where is it? Since we don't know really where's the entire tile map, need a better way to find it, I choose to understand better how the physics works on the game. If we understand how the physics works on the game, on the original tiles of the game, we can copy those behaviors to our tiles. Before understanding what attaches the Klonoa to the floor, we need to approach another important feature of GBA, the object attribute memory. The abbreviation is just OAM, and I use it now from. Since the GBA is a hardware to play games, it has many features to work well with games. One of these is OAM. It looks like a tile, but you can move it, change its sprites, size. And using a tool from Nocache GBA, we can see the the address in which Klonoa is stored on the memory. It's stored at this number. Read again the DMA logs on Macabeus, we can see exactly the batch that she writes on Klonoa OAM. So the batch from this address are copied to the Klonoa OAM, and the value on OAM that defines the Y position is the first. So we need to track the changes on these bytes 303004800. A very simple and useful test that I made to check if I am going to the correct way was change this batch and run a frame. Do it, we can notice that it changes. We can notice that it changes, but for just one frame, because on the next frame we will continue to fall from the previous position. So we can notice that we are going to the correct way, but we need to find the data source of this byte. So let's see some important assembly instructions that changes the value of this byte. On the first part, we can see some assembly instructions written in ARM. And on the second part, we can see the memory. The highlighted byte is the Y position of Klonoa. After these instructions, all bytes on this memory region are replaced by trash, including the Y position. And the main instructions after that, the Y position is replaced by the new value. But how? How did it work? Since we have just trash on this memory region, how could it calculate the new Y position? To understand it, we made some crazy reverse engineering using both tools, Macabeus and IDA. With this analysis, I found an important detail. The byte that I was following from OEM address I used to set the new Y position to the camera, but the byte on the left I used to set the global Y. For example, in this image, you can see that Klonoa is on the same height to the camera, so the values are same. But since it's on a higher position on the level, this value is lower. So we need to follow this byte to understand how it's updated. Run step by step with the bug, we found the moment when this value is updated. It happens on the assembly instructions in this block. And the decisions of whether it should update or not is made in this upper block. Zoom in the upper block, we can see how it decides whether the Y position should be updated or not. And these instructions use a type of storage in memory region, in another memory region, the slow WRAM. This another memory region is bigger than the fast WRAM, so the game can store the entire time map in this memory region. So we should add our tiles. Our tiles to slow WRAM because it's the data source of slow WRAM and VRAM. And do it. Our tiles really works. We can stay on it. And our tiles don't disappear when they are outside of the play vision. But okay, very nice that you can create real tiles on the game, but we want to create an amazing level editor on browser. So we need to find the tile map on the ROM to be able to extract it and deploy it on the browser. It's one of the most important reasons that one should have at this project. Why the information flow has this way from the cartridge to slow WRAM and the fast WRAM to VRAM and to display, you are walking on the reverse way. Use the clues that we will find on the path to walk from display to slow WRAM. And because there isn't any memory region before slow WRAM, we need to use the chips to find where is the tile map on the cartridge. So let's run the step-by-step debug to see the instructions written on the tile map to slow WRAM. and we find the instructions SWI118. But what the fuck is it? So let's talk about SWI instruction. There is software interrupt. Some guys call it as BIOS call. Well, BIOS is a firmware that is intended to initialize the physical components at the system. In GBA, its BIOS exposes many functions often used in the games, including data compression and decompression. Each function has an associated numeric code, which must be used as a parameter in the SWI statement. For example, there is a SWI code to use the divide operator. To call it, you just need to use the SWI with the number 6 and send the parameters to the registers. And the R0 is the numerator and R1 is the denominator. And the output of the divider will be saved on the registers. Besides the divider operator, we can call some compression and the uncompression operators the SWI code instruction. For example, here the game is called Huffman and LZ77 algorithms. And the Huffman and LZ77 algorithms is a deflate. So this game, when it's loaded a level, uncompress it use deflate algorithm and save the result on slow double run. Follow the parameter with the address of the memory data. We can see the compressed data of the level. Either is so awesome that you just need to push the cursor at the address and you show the entire blob. And you can use a feature of either to export this data from ROM to a separated file. Okay, now we have a file with the compressed data of the level. Then we need to uncompress it use the same algorithms of the game. Do you remember that Matheus said that Gameboy Advance was a very popular console and many people made awesome tools to work with it? So a person made a few years ago an open source tool written using C with the same algorithms and implementation of the compressed algorithm for the GBA. In order to use it, we just need to send a file path to the software that will uncompress the file. And use it, we can note that the byte from cartridge and from the uncompressed file are the same. Okay, now we know where the tile map is and we have a file with this data. But we want to create a maze level editor. So we need to paint this tile map to be able to edit it. But we have an additional challenge. We have just a vector with this data, and we need to plot it as a bidimensional array. For example, all these plots are valid, but just one of these are used on the game. So we need to find the correct one. Where's the new line from this vector? And we have an important clue to help us. The size of the buffer, and probably the height and the width are natural numbers, because it don't make sense a half tile. So we just need to find the height or the width, and we find all the variables. Think with me. I am on the tile A, and there is a tile B exactly below A. From the tile A to B, there are 9 bytes. So there are 9 tiles. So the length of the tile map is exactly 9. So we can reproduce the same idea on the game to find the length of the level. Firstly, we need to get the address of the tile A. To get it, we need to set a breakpoint on this instruction. So we can see the address of this bridge tile on the registers R0. Then we need to mark this tile, change it. So we should change this byte. This is our tile A. Then we need to drop Klonoa one level below in order to get the address of the tile on the second level. To do it, we just need to change the tile below him to 0, 0, and we can see Klonoa now is one level below. And as the last step, we need to get the address of the tile B. And we know the tile B is near him. We can find this tile, change the tile around it. Because we get the address of the tile A and B, we can subtract to get the length of the level, that is 420, and divide it with the entire size of the buffer. We can get the height of the level, and now we can plot it, right?
But yeah. But before develop the web app itself, it was very important for us to, just have a basic proof of concept that allows us to know that what we were doing, we were going on the right way. And so to do this, we decided to plot what we had on a BMP file, and to do that, we used Jump, which is a open source library in JavaScript. And actually, here we are loading the libraries and the tile map, and we sort of dropped the first 3 bytes because they are not relevant for this. They were headers, and we then paint with white if the code is 0, 0, and otherwise we paint with black. And the code, and here we are looping for everything, and for each byte on the tile map to paint each pixel on the BMP file. And actually, don't mind this code. This is a very, very poor code. It was mostly for us to just test the idea. And with it, we can see the entire tile map on the screen. So yeah, yay. This was the first level. And there's this scheme in the corner. And basically, it shows all the tiles available. And to be sure that everything was going just like we wanted, we then painted the other levels. For example, this is the second one. And by doing a very, very boring process, we then started painting with colors. So you just examined each tile and each color and mapped them to, just to get a prettier tile map. So this is what things started looking like. And I think that we better show how it works now.
Okay, now we want to show to you the site that we are building.
Yeah, live coding stuff. But this is what the platform looks like, and here I can browse the files to try to find a new ROM. And basically, here I have a few ROMs. I'll start with the original Gameboy Advance ROM for this game. And once I load it, I have to select a vision. Vision are the levels in the game. So I'll just pick vision 1. And this is what the level looks like. And actually I have a few other options like showing grid, for example, and showing or hide the OAMs for the character and the enemies, and the same for portals. But let's try, and I can inspect things. For example, if I click a tile, it will tell me what this tile is. For example, tile rock, and its ID and position. And we can start by just trying to, paint something different. So on top of this grass, I will add some rocks here. And then I can save the map. And I'll call it modified 1. There are certain Game Boy Advance emulators that we can use. For example, there's GBA.js, which is an online one, but I'll use MGBA, which is one that runs on Mac. And I just load the ROM here, and I'll choose modified 1 GBA. And I hope this goes well. Again, we just removed the game songs because they are annoying. but yeah, they are. I just select the level, select the vision, which is 1.1, the one that we modified. And as we walk, I can see the tiles that we just added. If you guys remember the tile map opened on the game, they're pretty much this one. And we can do some more complex stuff. For example, no, this one. I painted the conf, and let's see what it looks like on the emulator. MGBA. Our file, load the ROM, and it's called modified2.gba. And again, yeah, you guys gonna see this again. No data. Come from. I tap. Select a vision. Start playing. So I'm terrible doing this. But as you can see, here I have the conf painted on the game tile map. And I can play the game regularly. And yeah, that's pretty much what the level editor is. But I better stop mirroring. So yeah, this was the project, and telling you guys a little more about how we made it and the coding part and the web application part, which is let's start by this stack. So as I mentioned earlier, this is a React.js application because basically we work with React and we are used to doing that, so it was the faster way for us. And also we like all the React.js things of having of building things declaratively and the way we can handle state. And it's a major library with a good environment. We also used Webpack for doing some complex setup stuff that I'll detail in a minute. Of course, Lambda, because it's the utility about the hyped utility about. And we really like the way it does currying. And the currying that Lambda brings just plays very well with the pipeline operator that you can get with a Bubble plugin. You guys will see in a minute. As a UI library, we picked FormaKit because it just has many components that we had in our UI mocks, so and the core-based layout thing too. And it was a static site, so we deployed on GitHub pages, but it could have been any other thing like Surge or NowSH or whatever. A few highlights on the architecture. Yesterday we saw many talks on monorepos, and we also like the idea of monorepos, so we applied this in CloudGBA.js, and we have two projects inside it, which are Brush and Scissors. And basically, Brush is the responsible for the UI. I mean, it's the React application itself. And Scissors are a bunch of utility functions for handling the game run itself. So, for example, Scissors is the one that extracts data from the game, and Brush is the one that renders the tile map and all of those things. And inside Scissors, we have the definitions for each level, and they are all JSON-like files. And basically, they look like this, where we have the ROM object, which contains the OAMs and the tile maps and portals and all of those things. And the most important part is the tile map object itself, because it's got height, width, and details of the level. But it's got the scheme object with the scheme array, which is basically an array of objects detailing each tiles that we can have. For example, grass, rock, dark rocks, woods, or whatever. And they have the memory addresses, and this is what the whole file looks like. Another thing to mention is that we applied the famous provider pattern that we have in React. So we needed global state, and we have many solutions for this, like Redux, Mobex, and so on, but they were not necessary for this app, so we went with the context API that React has got since 16.3. And basically, we have two providers, which is the ROM provider and the vision provider. And as you may guess, ROM works with the game ROM, and Vision takes care of everything that the user is seeing on the screen. And React.create context, some basic React stuff. And this is how we use them. Basically, we have use context, the hook, and we pass our context, and we get data, for example, the word and state of the vision, and so on. Since we're talking about hooks, it's cool to mention that we have some custom hooks, because this project started back in October 2018, and hooks were the thing in React. They are still the thing in React, actually. So we decided to play with custom hooks, and there are two that we'd like to highlight. The first one is, for example, use when vision changes, and here we use context and use effect to have a hook that basically notifies the view whenever the vision user selects another vision. And also we have more complex hooks, like this use tool, and this is a hook that has like 35 lines of code, and yeah, I had to split in 3 slides. And for example, we like to highlight it because it's a complex slide as logic, as I mentioned, 35 lines of code. And with those custom hooks, we can isolate well complex side effects for logic in a reusable way. WebAssembly, this is my favorite part, talking about the stack, because actually we have this. We have the compressed tile maps that Macabeus mentioned, and we have that old C code to uncompress them, and we get the decompressed tile map that we need. But there is one gotcha here, that is we can't run C code on the browser. So how would we do that? Yes. We could try to translate the decompression code to JavaScript, but that would just take a lot of time and extra effort that we didn't want to, because our initial idea was not learn more about C. So our way was to use mscripten, and basically mscripten generates WebAssembly code, so mscripten to the rescue. And what we have is the Huffman.c and there's the LZ77 files, which are the 2 algorithm decompression codes. And we run mscript on top of them, and we get their WASM files and JS wrappers to make it easier to use them. But then a few problems come. So aiming the cache stuff on browser, for example, Webpack sort of he named the assets like some handle hash string dot something, and our JS files were just looking for that wasm files. So in order to go through this, we had to use a custom a file loader and to handle the wasm files. And in this part of code, there's also another gotcha. If we scroll it, we see this line of this line, and this line is there because basically we didn't intend to modify the original C code, because as I mentioned, it would just take a lot of effort. But for example, we had to remove the main function. As you know, C code, we have main functions. And the main function from the original library was just calling some unnecessary codes, like tons of console logs on the browser, for example. So we removed the main function, but then the code stopped working. And in order to make it work, we had to use this workaround, which is that on runtime initialize and assign an empty arrow function. And this is basically how we compress things. We have the compressed file, and then it overrides the original file on compressing it. And as you can see, all the communication is based on the file system, which is quite puzzling at the first sight, because you think, how is the browser accessing the user file system with no permission? This just sounds quite unsafe. And what is happening here is that we mscript and just brings an abstraction over the file system, with works just out of the box. I don't know how, but it does. And here we move the buffer from the ROM to a file called file, and then we uncompress them. We also had to build a small shell script to make it compile things using Docker. The good thing is that there's a Docker image by the amazing mscripting community. And we just have to pass some additional configuration, for example, telling it to include the file system. And in the end, we just Docker run mscript Huffman and Docker run mscript LZ77. And that's what to get a 3 lines function that reads the ROM and pipes the results to the 2 decompression algorithms. And this is the pipeline operator I mentioned earlier using the Bubble plugin. Last but not least, the tile map. As you may wonder, the tile map is the most complex thing in the UI, because basically it displays the tiles and the OAM, and it allows the user to edit them. And the first version we used Canva, which is a library on top of the Canvas API to render the things. But by using Canvas, we were having some perf problems, and there's this GitHub issue that was our first perf issue. And to summarize it, the first load was taking 3 seconds, and the other loads were taking 13 seconds. And no, this is unbelievable. It can just work. And then we just did some React.js performance work, and we then went to 1.8 seconds, and the second load was taking 3.6. And by React.js performance work, I mean just removing extra re-renders and unnecessary re-renders and wrapping things with .memo and so on. And then we had this. And the next step on performance was switching from Canvas to WebGL. And then we were getting like 1.6 seconds and 2.8 seconds. So a huge improvement. And then we did some more optimizations on top of WebGL, and these ones took us to less than 1 second. So the first load was taking like 60-25, and the other ones were taking something around 500. So doing a perf recap, we started with this, and we thought no one's gonna use it. Then the performance work on React, we went to 1.8 and 3.6. And we got to 0.5 or 0.6 by just removing things that we had in React components to raw WebGL stuff. And the results, I just showed the result in the web app itself, but it's good to mention the results in the community. Since our first goal was to have a proof of concept for people to test, to play with, and to give feedback, as soon as we had it, we started spreading the word in Twitter, Discord channels, and those gamer things. And people started sharing what they were doing, and they were doing some amazing stuff. And also they had questions and other good feedback. And they started making custom levels. For example, this is one of our favorite. This guy is a speedrunner, and basically he made a level where you can't go through if you don't try speedrunner techniques. So yeah, people were doing this kind of thing. Talking a little about the future, we intend to be always improving the code base, and one of the things that we want to do is split it in 2 new React components libraries. The first one is React Exa. And the second one is React Tile Map, which we intend to be something that you'll be able to render tile maps regardless of the game, which is a generic schema. He is Macabeus, and he's a software developer at Logi. He's doing some full stack stuff, and he's the guy who's always trying some mad science stuff. I'm Matheus, and right now I'm a front-end engineer at TRV. And I'm the guy who's addicted to emojis, memes, and beer, so reach me out for the AfterConf. This guy is Raul. He's an illustrator, and he helped us with the game logo and part of the branding, so kudos for him for it. And this talk is available on a speaker deck, both mine and Macabeus. The project, as I mentioned, is open source on GitHub. You can find it at Macabeus/CloDBAJS. And also, there's a series of posts explaining in details how this whole thing went. The posts were originally written in Portuguese, but we are translating it into Spanish and English. This is the link for the first part in English, which is basically the introduction. Last but not least, we got stickers. So find us in the conference, and with questions, feedback, and all of those things. That's pretty much what we had for today. So thank you, guys. That's it.